Nice job. And I can't hand you the shirt that I have bought. And also, I haven't bought it yet, but I know how to. If you are willing to send me your address by email where you'd like it sent, I will have it shipped from the printer, and it'll come to your house and you can wear it and tell us how you like it. Also, information on size would be great too. I often guess terribly about that and buy smalls for people that are large and extra large for people that are small. So you can just send that privately if you want. Okay, so congratulations to all the winners. Let's give them a hand. Really nice job and beautiful fractals. Okay. So moving along, let's talk some about what we want to do today. Let's see. So today I want to talk about computational complexity, so asymptotic analysis. And this is something you may have seen a little bit of in 201 or another class like that. What I found is that students have some grasp of this sometimes, but often when I go into details, they would like to know or should know where this comes from. Like, why is that? How do you derive it? Is it more than just some recipes that you apply? So here we'll talk about the foundations of it. You can apply it deeply in this class. So the basic idea of this is, and by the way, there are good handouts today that are on the web. The lecture notes are on the web. There's a good section of Abelson and Sussman and an additional handout as well. So take a look. So today I want to talk about understanding the resource requirements of our programs. So basically in this class, we're introducing you to a lot of math, a lot of CS, and there are many things we're telling you about, and the level is appropriate, but there are many things for which there's an upper level class or two about. We're not telling you all of the details, but this is an introduction. This is an introduction to mathematical computer science. And so we'll do some things in more detail and show you lots more examples, of course. But the idea is to expose you a bunch of math and CS techniques so you can use them and become comfortable with them during the term and in your career. So we've been reasoning about programs in this class, obviously, think computationally, if you will. And we talked a lot about correctness. So a program that does the wrong thing is completely useless. And so we learned and are learning how to prove that programs are correct, reason about their correctness using substitution model plus mathematical induction. And today we'll start talking about efficiency, because a program that does the right thing but is way too slow isn't very useful either. And this is sometimes called the analysis of algorithms. So what are the mathematical tools that let us reason about correctness and efficiency? That's what we'll start today, and then we'll apply this. So we've done a pretty good job getting started on correctness, and now we want to develop tools for reasoning about efficiencies. So the goals are, we want to be able to determine rigorously the space and time requirements of our algorithms. And for many people that are working on algorithms or working on systems, this is one of the cruxes of computer science. It has kind of a strange name. So the term computational complexity, this was named by Juris Hartmanis. So the great Lithuanian computer scientist, he was my chair when I left MIT to become an assistant professor at Cornell, immediately won the Turing Award, followed by John Hopcroft. So it's a strange term in a way, although I kind of like it, because why is it odd? Because a very simple algorithm that takes a really long time would be called, complex. On the other hand, some incredibly Baroque piece of code that was unbelievably efficient, if you could analyze it, would not be called complex. So it's sort of a strange term, but we'll talk about what it means. So complexity is typically measured in terms of the size of the input, typically n, but it could be something else. We'll definitely see that right away. So for example, if we wanted to sort a list of all the students in the class, how fast can you sort when n is the size of the list? So we'll do a lot with numbers because that's kind of where we are in the class, but if n is a number, the representation matters a lot. And this is where we get almost into philosophy. So in particular, when we think about this, you have to know whether size is measured in terms of the magnitude of the number or the number of digits. So the magnitude of n is like how big is n, but the number of digits is different. It's important to know which, because they differ a lot. So they differ actually by a log factor usually. So you only need log number of bits to encode a relatively large number. So we have to say what we're doing there. To beat a dead horse here, if we have a huge number like 10 to the 20th, try to write that in the unary, you'll be here for a long time. You'll probably finish by the time you graduate, but it'll take a long time to write out 10 to the 21s. And it's even a lot in binary as well. So is it the number of digits or the magnitude that we're going to be talking about here? So today we're doing the analysis in terms of the magnitude of the number itself, but often we measure the number of bits instead. So what we want to be able to do here, we want to be able to compare the efficiency of algorithms or programs independent of a given machine or a given input. And until Hartmanis and Cook and Hopcroft invented this idea, the only thing people could do is take their program, run it on some machine, and publish a paper about it. And then some other machine might be faster or slower, some other computer might be faster or slower. And it was hard to disentangle or deconvolve whether the algorithm was better or the computer was better and so forth. But we'll have a machine-independent way to talk about how fast algorithms are, how much space they have. So our quest is to look at resource functions like R of n here. So R of n is a function that measures the resources required to run your program on an input of size n. And what we're interested in doing is what's sometimes called asymptotic analysis. So we're interested in how these functions of resources that predict resources behave as n gets large. Not the infinite limit, really. We want large but finite. So let's just recall what an asymptote is. Here's our little function here. We have y equals the square root of 1 plus x squared. Nice little function from calculus or something. And if this, I'll draw this, we have these asymptotes here at x and y. Looks something like this. And it goes, but I have hyperbola for you here. So rate.
Professor Donald, there appears to be an issue with your sound. It's really breaking up. Maybe he's left us. All right, everybody just hang tight. Okay, it looks like he's aware of the issue. That's good. Thank you for paying your respects in the chat. Very thoughtful.
How about now? Can you hear me now?
Yep, you're coming through.
All right. All right. I'm really sorry about that. Internet is connectivity is a problem. What we're going to do is we're going to back up to whatever we missed. Let's see now. Very sorry about the problems. Okay, tell me the last thing that you all heard, and I will go back.
I think it was just about the time you started talking about asymptotic behavior.
Right. Thank you. Appreciate it. So I wanted to use the example of a simple function to illustrate asymptotic behavior. Let's look at y equals square root of 1 plus x squared. And then to save a little time, I have a drawing of that prepared. Here's a general case of this function. In this case, set a and b both equal to 1, so that this asymptote here is y equals x, and this asymptote here is y equals minus x. So the idea, as x gets larger, you get closer and closer to the asymptote, namely y equals x. You don't actually reach it in finite time. And so as an example of this, we can actually plug in some numbers to get comfortable with the idea of an asymptote. I've made a little table here of y's and x's, so that you can see that as x gets bigger, y gets very close to x, doesn't quite get there. And this is something you may have seen. You may have seen this in calculus or in engineering or other places like that. So we're interested in a kind of asymptotic behavior as a metaphor. So basically the way we think about it here in this example, let's go back to our hyperbola, is that these asymptotes, these dashed lines, are things that you approach as x goes to infinity. So the way we usually write that in, say, calculus, we write something like the limit as x goes to infinity of 1 plus x squared is equal to x. Okay, so we're going to generalize this notion of asymptote to mean an approximation that gets closer to the truth in the limit. Okay, so that's the idea here. So these functions, basically, they might have different rates of growth. So, and that's what we're trying to capture here. So the functions, x versus x squared, these both go to infinity, but the thing is x squared goes there a lot faster. So one way we can capture that is the following notation, which comes from mathematics. It's where this complexity theory stuff started. It's basically we read this as grows more slowly then. So we'll write something like this. You have two functions. We're going to say f grows more slowly than g if and only if the limit of f of n over g of n equals 0. And in the rest of this lecture, all limits will be taken as n, or whatever the variable is, goes to infinity. So this is pretty nice. In LaTeX, you typeset this beast by \pred for predecessor. It's kind of this scripty thing here. I'll write it like this in text, and you may too, but beware that that's used in other places, used to have other meanings in other branches of mathematics. So using this, you can pretty quickly prove things like this. You can prove that the constant function grows less slowly than, grows more slowly than log n, which grows less slowly than n to the c for some constant c, which grows less slowly than c to the n, which grows less slowly than n to the n. And so we can rank the functions in terms of how fast they grow in some sense. So in order to get this behavior, you have to think really big. So for example, here's an example here. If we have we know that we sort of think that log n grows more slowly than n to the c. Here's an example of what's c. Let's look at log n down here, n to the 0.001. So, if we just plug in numbers, we might not have it. If we try a equals 10 to the 100th, we don't actually have that log a is strictly less than a to the 0.001. But if you go big enough, you'll get that. Let's take b, which is 10 to the 100th. Then log b is 10 to the 100th, and b to the 0.001 is about 10 to the 96th. So if you get big enough, these relations will hold, but you have to get really big for some of these things to actually happen. So you cannot, in general, tell when f grows more slowly than g by just picking a value for n and stuffing them into f and g, any more than you can figure out length of a fractal by looking at a given level. Only the limit thing really works for this. So this is a way of thinking about order of growth. And what we're trying to do here is to use a notion like this to capture important differences between the growth rate of functions. That's what we're trying to do here. So why do we want, by the way, why isn't this funny scripty less than, this pred or grows more slowly, why isn't that enough? Well, in some sense, it doesn't do quite what we want. So instead of this, we have this order notation you may have seen in 201 or other classes, or 101, functions of the same order, like order n squared, and so forth. And basically, the issue is that this sort of grows more slowly or pred relationship, it's a little too strong here. So for example, using this relationship, we might we can immediately look at two functions like x squared plus 1 and x squared plus 2, and it's not the case under this that x squared plus 1 grows more slowly than x squared plus 2 under this definition, right? So that's kind of a little bit unsatisfying. By the way, what is the actual limit here? Remember, we have a formal definition of what this is. We want to know if the limit of x squared plus 1 over x squared plus 2 is. Yeah, Tommy texted, or rather chatted, the limit here is 1. So it's 1 and not 0, so the definition wouldn't be satisfied. So we could try to do some really weird thing here. We could try to say, well, let's have a definition where the limit of f over g is some constant. There's a branch of mathematics that does this. And this generalizes our notion of pred, and it also handles this particular case here. What we're going to do is a sort of slightly stronger condition, and you can ask yourself how so later. That will be kind of a thing for you to consider. And this is our definition of order notation that we'll use in this class. It's the same one you might see in other classes as well. So basically in this definition, I want to say that f is order g, like this, when there's some constant c such that f of n is less than equal to the constant times g of n for all n greater than equal 1. And this means conceptually that f is at most g. It's kind of like a less than or equal to kind of relationship here. Now, this is often written, even by me, as f equals order g. And you're going to see this, I'm going to do this even now. This is completely an abuse of the equal signs. It's in no way an equality. And careful people write this as f is in order g, because order g is actually a set of functions instead. But I will still say it this other way because it's convenient, and you'll see that a lot. Okay, so this is our definition. We're going to use it some now. Here's a function. F of n equals 1/4 n cubed plus 27n squared plus n plus 1,000. So here's this thing here. Now, this is an interesting function here, and it is, look, I've already done it. If the order of growth of f is n cubed, because the n cubed term dominates it. How could we prove that using the definition? We're going to slavishly use the definition. There has to exist some constant c, such that f of n is less than or equal to c times g of n for all n greater than or equal to 1. So you could actually take this, and there'll be some exercises maybe where we work out those constants. So we could, for example, determine that 1/4 n cubed is less than some constant n, that how do we determine this n cubed? 1/4 n cubed is less than c n cubed when c is greater than or equal to 1. 27n squared is less than c n cubed whenever c is greater than or equal to 27. This is a huge amount of work, and and we want to have some shorthands, shorthand for doing that. Yes, you can definitely do a set membership, Dominic, but it's not used very frequently. Technically, it's correct. It'd be considered a bit pedantic, but that is the correct notation if you wanted to do it. So we want some rules to this, prove them once, and then use them in other places. So here's some rules for manipulating order notation. How about proofs? So you should try to prove all these correct. We'll do a few in recitation probably, and then use them. But state them, and then I want to use them a little bit. And I'll prove one of them at the end if we have time, the one involving logs. So here are some rules for simplifying these things. And notice I'm motivated by this polynomial example. I mean, this thing here, this polynomial is kind of a bear, right? You have all these constants and stuff. How do we know this is in order n cubed? And this answers Dominic's question. N is just a synonym for set membership, right? But we typically don't actually say that just for cultural reasons. How do we know that? Well, we want some rules that will simplify it so we don't have to make up these constants each time. So you're always welcome to do the constants. It's just time consuming. So the first is like this. Suppose I have a function, r times n to the a. Well, this thing, when is this thing in n to the b? Well, that's true whenever a is less than or equal to b. And this is true for any r as long as r, a, and b are independent of n. If they grow at the same rate as n or as a function of n, then all bets are off. You need a different rule. So this basically says that, you know, a polynomial is order of some higher polynomial if the polynomial has a higher exponent. Now, consequently, we can prove using this definition that n squared is order n cubed, but it's also order n to the fourth. In fact, it's any order larger than n squared. So in this game, we always want the least bound, which is n squared. That's the smallest polynomial. Second rule is that order f plus order g equals order f plus g. And these two rules will simplify that polynomial example with the 27n squared very easily. And they're not hard to prove. We need an identity. F is always order f. And here's one that's kind of pretty nice. If we have two constants a and b, then they're the same order. Order a equals order b. We also often write this just as order 1. And this will also signalize that you're a computer scientist, because only computer scientists do this, although it's correct. Now here's a pretty cool one. And I think this is the only one that's maybe worth proving together. I'll try to do this at the end of the class if the internet holds out. So log b of n is just equal to order log n, and we don't need to write the base down. Why do we do that? Why is it independent? So different fields, different parts of mathematics use different bases. So computer scientists, of course, like to take logs base 2, like log 8 is 3 and so forth. I think mathematicians in my department like base e a lot. Engineers probably like base 10. But for order of growth, it doesn't matter at all. And they differ just by a constant. And we'll prove this at the end, or at least maybe we'll do that recitation. But let's look at one example where we're comparing the log base 2 to log base 10. If we have log base 2 of n, we can rewrite that as log base 10 of n times constant, which is log base 2 of 10. So this is just a constant c. The whole point of this is that we want to obscure constant factors. So log base 2 of n is simply just order log n. So no matter what base you put a logarithm is, it will only differ by a constant from any other basis. We just write order log n. And we'll do an example of this later. And finally, this stuff is pretty old. I mean, you know, it's true that no one writing papers likes to cite anything before the year 2000, but this stuff is basically developed in the 1800s, even before there was even computers around. Okay, so we have this definition of asymptotic complexity. It's exactly the order notation for time complexity that you might have seen in a previous CS course or maybe mentioned, except we now really know what this creature is. And with this at our disposal, let's look at an example from a very recent lecture, namely times 1. So this is our recursive definition of times 1, right? And it basically computes multiplication by repeated addition. Okay, recursive process, of course. Sorry to hit that. Recursive process here. Let's compute the order of growth of this function times 1. And we want the resource function, you know, r of n or t of n in this case, we want it to be a function of b, which is this integer here. Function of the size of b, the magnitude of b. So we want to figure out the time complexity of this, t of b, as a function of b, this parameter here, to think about how to do it. So let's make a few comments about this before we kind of do some stuff. I'll go to the document camera in a minute. So the operations in this function, there's several that are involved. We have the operation times 1, which of course is non-trivial, and then a lot of built-in stuff like plus and minus and equals. So what I'm going to assume here in this class is that all of these built-in functions like minus, plus, and equals, these are all constant time or order 1. Remember, I don't care if it's order A or order B, as long if B, A, and B are constants, we just have order 1. So they run in constant time. Now, this is safe for now in this class, but some primitives are not constant cost. And this is a point that some students forget when doing their research or when doing problem sets and exams. And we'll show you some of these next lecture. And there were a few perspicacious students who noticed that there were functions that they asked to use on problem set 2 that actually might not be constant time. And you have to know how expensive they are. And this particularly is true in powerful languages like Scheme, where a little function could actually end up being very expensive because it's doing a lot for you. But today, all the built-in functions are going to be constant time. However, times 1, of course, is some kind of recursive call, so you can expect to see some kind of recursive thing going on here. Finally, I want to just point out that even for arithmetic operations, assuming that all of these pluses and minuses and stuff, these are exact and constant time, is not quite correct. And for that, you'll have to either take a computer algebra course, and you'll have to also, or take a numerical course too. Yes, we'll assume that times the times function is, i.e. the star built-in multiplication is constant time. So all of the so-called field operations for the real numbers, the plus, minus, times, and divided by will be constant time here, as well as equality testing. And if will be constant, if tests and various things like that. So we'll assume that for now. So how could we figure out the complexity? Well, we could trace through the substitution model, and we could count calls by hand. This is quite a pain, right? We don't really want to do that. So instead, what we're going to do is we're going to try to look at this as a recursive process. And what I want to do instead is I want to try expressing the running time as a function t of b, and expressing it recursively in terms of other calls. So the same way that the value of times 1 can be expressed in terms of the value of times 1 on lower values of b, the time complexity of times 1 can be expressed as something plus the time complexity on smaller values of b. And if you think about this, the time complexity when applied to 0 is some constant, as I've shown here. The time complexity when applied to b is going to be some constant amount of work, because a bunch of constants add up to a constant, plus the time to call yourself recursively on b minus 1. And we can see that directly from the code here. Here we have, recursive call. This is your time on b minus 1. And everything else here is constant, some constant order 1. So the equals, the testing here, the logic, the plus, the minus, these are all constant time. And so that's why I've been able to express the time complexity here. I haven't solved it as a recursive function. T of b equals t of b minus 1 plus c when b is greater than 0, otherwise t of b equals c. And the c's are just order 1 constants. This is a fundamental concept in computer science. It's called a recurrence relation, because we are basically expressing the complexity in terms of something smaller. And at this point, I want to point out that sometimes we can actually solve these in closed form. And I'm going to do that now with the document camera. So assuming the internet holds up, we're going to take a break and move to the document camera. But the break won't be very long, so don't go far. Stop broadcasting. Turn this off as I move. I'll be back with you in a second. All right, I'm back. I'd like to ask, can everyone see the document I have here in my hand?
Yep,
And,
can see it.
okay, good. Thank you for your patience. It's not the fastest setup to switch, but it's it's reasonably good. And I don't think it's too bad to have a break in the middle of a long class like this. Okay, so I'm going to do this one later. We have 2 versions of the times function. Let's look at times 1 again. So I just put it here. It's a real paper clip. It's not a metaphor. And let's try to think about solving this recurrence relation. So the way I like to think about this is, let's put up our recurrence relation again. And that's a term worth writing down. To C of 0 equals C, because when you run this on run times 1 on B equals 0, it does a constant amount of work to return 0. More interestingly, T of B is equal to T of B minus 1 plus C when B is greater than 0. Okay, good. So let's just take this down here and try to solve it. So let's expand that. So let's go down one more level to get some intuition. Let's go down one more, get T of B minus 2, reaccumulates another C. And we can keep doing this for a while, and eventually we'll get something that looks like this because we'll hit the bottom. T of B minus B plus a whole bunch of C's. Now, how many C's? Well, we'll do this B times. So it's kind of like a, sort of like an inductive proof here. So this then is equal to T of 0, because B minus B equals 0. I'll just collapse this to, I'll just collapse this to B, that's a plus sign, to B times C. Now, how long does it take to do T of 0 here? Well, we look up here, T of 0 takes constant amount of time C, so specific constant. So this then simplifies to B plus 1 times C, and that's equal to order B. So our function times 1, we can solve the recurrence. It takes order B time. In other words, it takes time linear in the magnitude of B to compute an answer. Not that surprising, but notice this is a recursive process generated by this syntactically recursive function. And moreover, we could prove it correct and have proven it correct using induction plus the substitution model. And our proof here of the complexity being linear time, i.e. order B, is very similar in flavor to an inductive proof. All right. Any questions before I go on? So one thing here, now that we've proven this is a general pattern, and we can use it lots of places. Let's just call it pattern 1. And this is also on the web. If we have some recurrence relation, T of n equals T of n minus k plus C, where k is a constant, and of course we have T of 0 equals C. This is order n, where k and C are constants. Notice if your k and your C, if these guys depend somehow on n, you have to do a different kind of analysis, but that didn't happen in this case. All right, so we've done our first proof of complexity. We've done our first recurrence relation in this class. And now I want to do something a little more challenging. Why is it B minus 1 at the end? What I did is it's B minus 1 because I just collected the terms here. This is because T of 0 equals B. That's where the 1 comes from. So I'm just basically, I sort of have this policy of working everything out from you in the beginning, but to demystify it a little bit, there's some actual conceptual steps like this one, which is, pretty reasonable. But there are other steps which are just doing the algebra. And I probably should just declare when I'm just doing the algebra so you can just check it. But feel free to ask questions. Yes, this is order B at the end. Order B. And by the way, I've also typed this out in the lecture notes. So if there's something a little unclear or internet problem or something like that, please look them up and let me know. Okay. All right. Shall I go on to a faster multiplication routine? Let's do that. And so this is important because we'll ask you to use this to prove the complexity of your programs. So here's a pretty cool way to do multiplication. It's related to some things you've been looking at. I call it fast times because it's going to be, surprise, surprise, faster. And this uses a paradigm that's sometimes called divide and conquer. Which we'll see quite a bit in this class. All right, so there are a couple of beasts in here you might want to think about. There's double. So we defined double last time. Double multiply something by 2. We haven't defined half, so let's do that. So we'll say define half. Lambda x divided by x2. So this function that cuts something in half. Now, as before, I'm going to assume that all the built-in primitives are order 1 or constant time. So I'm going to assume that the predicate even, equals, plus, evaluating 1, of course, minus, all these things are constant time. And I also want to assume that double and half are constant time. Why is it reasonable for me to have double and half be constant time? Without loss of generality, you can just consider one of those. Why should the complexity of doubling something not grow with the size of A? Why am I saying that? So they do invoke a primitive operation, which is true. But as I mentioned, you could imagine having some fancy functions that actually grew with size. And I sort of claim that you still could do double and half rather quickly. So in fact, if you go into Scheme and you try to multiply 2 really huge numbers, it will actually return what's called a big number, big num. It will actually take longer to multiply them. So it's a question about realism in some sense. So yes, double and half do indeed involve primitives. And so you might assume these can run in constant time. But in a way, you know, multiplication, we sort of think of it, and division, you might question this. I want to sort of convince you that you actually could implement this rather quickly. So let's look at an example here. Suppose I had a number like 5, and I can encode this in binary as 101, right? It's an odd number in some sense. Number like 6, I can encode this in binary as 110. And it's back to how some numbers are encoded in the machine. So if I had a number encoded in this fashion, and I'm going to suppose without loss of generality, that it's actually an even number. So I'm going to have a 0 here. It might be encoded like this somehow. 1, 0, 1. Bunch of other bits here, 1, 0, 0, 1, just some arbitrary thing like this. And I want to look at half, which is going to cut this thing in half. And of course, I could always appeal to the fact that I'm calling a primitive operation. But to convince you this is reasonable, even kind of a hardware sense, there's a way to do this in constant time, even in reality. And the way that we do that is we put the bits together like this, separate them by a little bit of logic. And what I'm going to do is I'm going to put my 1, 0, 1, 0, 0, 1 like that. And what I'm going to do here is I'm going to put some electronics here so that when I gate this with another signal, that it will transfer the constants of this bit to that one. And then I'll put another one here like that, another one here like that, another one here like that. This is called a shift register. And this same signal work, I can actually do this all at the same time. Then I have a master signal coming in like this. So basically, it's like a bunch of dancers, right? Is that everyone's moving down to the right at the same time. So I put a signal in here saying shift to the right. At the same time, this moves to that moves to that moves to that, but they all do it in parallel. And so the result of shifting to the right, of course, is the number divided by 2. So most hardware is set up to do this even on modern chips today. And that's one reason why double and half, you can think of these as being very efficient operations. Have any of you seen that in an engineering class before? What did they teach you over in engineering? Okay, but anyhow, kind of a cool thing. Does this make sense? Is it kind of fun? All right, well, so in that case, we have 2 explanations for why double and half are constant time. One is that we follow the definitions that they have used a primitive, which is going to be constant time. If for some reason you didn't believe that multiplication or division were constant time, you could assume that you had a shift register like this, which would shift all the bits to the right, therefore dividing in hardware in parallel in constant time, which is actually how computers are actually built. Okay, so back to where, that was a little digression, back to where we were before. All the primitives are constant time, double and half are constant time. What's the complexity of fast times in terms of the size of the number b? So we can write down a recurrence relation for this. T applied to 0 is just equal to c. Now there are 2 cases, b is either even or odd. So we can say t applied to b is equal to t of b over 2 plus c if b is even and greater than 0. Why is this true? Look at this first case here. If b is even, then what we're going to do here is we're going to call ourselves recursively. We're going to double A and halve b. And so since we're measuring the complexity in terms of b, b got cut in half. And so even though A got bigger, B got a lot smaller. And so the complexity of doing this to B when it's even, T of B is equal to calling yourself recursively on an input that is half the size. On the other hand, when B is odd, we have something fairly familiar, namely the complexity is T of B minus 1 plus C if B is odd. Because here we have something similar to before. Basically, we call ourselves recursively on something that is only b minus 1 smaller. So the even case, which is very fortuitous, we're going to call ourselves on an input that is exactly half the size. On the odd case, we're going to call ourselves recursively on something that is only 1 less than the current size. And so we get this as our recurrence relation here. So the first step in solving these complexities is to write down the successful recurrence relation. And then the rest is just math to solve it, which we're going to help you master. Does everyone agree with this recurrence relation and see why it's true? That is T of B over 2 in the second line, correct. Thank you, Tom. If you have questions, please ask them now, because if they're about the foundation, they'll be easier to get at now, and it might be confusing later when I assume this recurrence relation and I just work out the math to solve it.
Why do we, is it just b over 2 because it's even and odd, b minus 1 because it's odd? I'm confused on where you got that.
Well, so basically, it makes sense there should be 2 cases, because in the con condition, there's an even and an odd case. Does that make sense?
Yes.
So I do different things. So it makes sense there should be an even and odd case. So that kind of comes from the code. And then I just ask what happens with the code. So let's look at the odd case first. In the odd case, it's just like before. I call myself recursively on something that is only 1 less. Does that make sense?
Yep.
Okay, now let's look at the even case. Here's the even case here. What I do is I double A and I have B, but B is my measure of complexity. And so when I call fast times recursively on this input, the input is now half the size. So the time complexity of the step to be done here is t of b divided by 2, because the input has been cut in half.
We don't have to do with anything with A because we don't have to double anything.
It's not a measure of the complexity. Like in this model, we can double it. It doesn't affect the complexity in this case.
Okay.
Yeah.
Is it possible to have more than two conditions on, like, if b is even or if b is odd? Like, if you had a different type of function, could you have multiple lines of the recurrence relation?
You definitely could. I mean, for integers, they can only be even or odd. I mean, well, in some sense, even or odd, and 0 is kind of a special case, although mathematicians consider 0 to be even for bizarre reasons. So it only makes sense to have two cases here, but yeah, you could have different ones, and then it gets more complicated. So very reasonable question. Okay. Let's see if we can solve this recurrence relationship. It'll be a little more challenging, but I think we can do it. So I want to start, this is something mathematicians do all the time. I'm going to start with the easy case. I'm going to start with the case where b is the power of 2. So we'll relax this. So what does it mean for b to be power of 2? That means b is equal to 2 to the log base 2 of b. Remember, I'm just solving a simpler case at first, right? I've got to generalize it, but we'll start that way. Another way of saying that is b is equal to 2 to the q, where obviously q is equal to log base 2 of b. And I'm saying this is a nice natural number. So it just means it's an exact power of 2, 2 to the q for something. So let's do this case first and try to solve it. I think that will be pretty nice. And then we'll generalize. So in the case where b is a power of 2, we'll always be in this step here. So let's do it. So t of b is going to be equal to t of b divided by 2 plus c. And that's exactly what the last question I think that Carolina asked was. Basically, in order to figure out the complexity, we're going to call ourselves on something half the size. We have to do constant work to set it up and do the call and receive the value. Let's do one more step. Suppose it's even the next time, which it will be because it's a power of 2. Then the next time t is b over 4 plus c plus c. We keep track of the c's here. And then next, let's do one more, t of b over 8 plus c plus c plus c. We're accumulating c's, but the b is getting dramatically smaller. This goes on for a while. Let's look at an intermediate value, t of b over some constant k. Now k doesn't have to be, so k I'm going to assume is the power of 2. It's just some other value like 2, 4, or 8. This will then look like, that's a plus sign, c plus c plus c like this, where there are a bunch of these. How many of these? They're going to be log base 2 of k times. And now we go all the way to the bottom and we set k equal b, and we have t of b over b plus, writing this again, c plus all the way up to c. And substituting b for k, we'll have log base 2 of b times. That's how many c's we've accumulated. And now, at this point, it's just two things. First of all, we notice that this guy here is t of 1. So we just have to do like, we don't have t of 1, we have t of 0 here. So you have to do a little bit of thinking about how t of 1 relates to t of 0, and then we have to do a little algebra to clean up. So the questions about why did the algebra work out, but it's just bookkeeping at this point, just collapsing the algebra. So let's do that. So t of b over b, this is clearly equal to t of b of 1, t of 1, right? Which is fine. And then this thing here, we'll collapse it as a multiplication. This will be log base 2 of b times c, because I've just done the repeated addition and done it like that. Now, pretty clear this is going to bottom out into constants. Let's actually do it. What's t of 1? Well, t of 1, you have to call yourself one more time, right? So, because frankly, 1 is going to be odd in some sense. So this is going to be equal to t of 0 plus one more constant. So 1 plus log base 2 of b times c. We're almost there. Now we can look up the value for t of 0 in a recurrence. It's also a constant. This then works out to be 2 plus log base 2 of b times c. There's a lot of constants in here. This basically is equal to log b as desired, because everything else is a constant. And so now we've proven that in the case where b is a power of 2, that fast times runs in time only logarithmic asymptotically in the size of b by solving the recurrence. And we have a very valuable pattern here. Again, this pattern is called divide and conquer. We basically are cutting it in half at each time we're doing this. And our pattern 2, which is more general, and now that we've proven it, we can use it. Our pattern looks like this. T of n, if that equals t of n divided by, let's use k again, since I used to divided by, say, p plus c, and t of 0 equals a constant. This is order log n, provided that p and c are constant. So now that we've proven it, we can use that anywhere we see this pattern. And it's more general than just dividing by 2. You can divide it up in smaller pieces as well. So now we have a proof that in the case where b is a power of 2, so we always call the even branch, that the complexity of this function is only log b, which is going to be much faster. Any questions on this?
How did you get from t of 1 to 1 plus log 2 of b?
It took three steps, right? Here's the t of 1, right?
Yeah.
Do you mean why is this line here true?
Why is the line after that true? Or like, why does the 1 get added to the parentheses?
Yeah, so what I did here is I expanded the t of 1. So to do t of 1, I have to do a constant amount of work plus the time for t of 0, right?
Mm-hmm.
So I just put the 1 in here for the constant, right?
Okay, thank you.
Yeah, it's just algebra. I'm not saying algebra is non-trivial. Definitely ask about algebra questions, but I want to distinguish between when it's algebra and when it's some deep concept that you might not have seen before.
How did you get?
Go ahead.
Oh, sorry. How did you get log base 2 b times? Could you explain that a little bit more?
Yeah. So basically, you can see the pattern here. Like as I cut this down, right? So here's b over 2, I get c. Right, b over 4, I get c plus c. b over 8, I get c plus c plus c. b over 16, I get c plus c plus c plus c. So that just generalizes to this being, so basically this thing here, right, this is always a logarithmic number of times that you're cutting the b down. Does that make sense? Like, look at it here. We have 2, 4, 8. Next time we'd have b over 16, which would be 4 c's. b over 32, which would be 5 c's, and so forth. So the pattern's just stepping through powers of 2 there. Is that intuitively plausible?
I think so. Thank you.
Yeah. If you're interested, I just gave you an intuitive explanation of this. If you want to see it in more detail, and that's a great thing to ask, you can back this up, the fact that this is actually log base 2 of k, using induction and the substitution model. And your trusty TA Omar has actually just written up our proof, and that's on the web under the lecture notes, that actually derives by induction and the substitution model that is log base 2 of k. But I want to concentrate on recurrences here. And for the purposes of this lecture, you can either see it intuitively, but if you have any doubts, substitution and induction is the way to prove it. And we'll give you a proof of that. It's already on the web. But thanks for asking. I should say, but thanks for asking, and thanks for asking. More questions?
I'm a little confused with how you jumped from the statement which says t of 1 plus log 2b times c to the next one, how you ended up with a t0. Did you just simply evaluate this t1?
Yeah, so, well, t of 1, that's when you're causing it, calling it a thing of size 1, right?
Mm-hmm.
So when you call it a thing of size 1, it doesn't bottom out right here, right? It's going to actually do the odd case here. So you do a constant amount of work. There's your constant there, this 1 times c, and then you have to call yourself recursively n t of 0, right?
Yes.
So that's what we're doing there. So
Oh.
think of what happens when you call this. Remember that this is a really nice case because b is actually not the size, the number of digits, actually the value of b. So that's what happens when you call fast times on a number a and an integer 1, b equals 1. In that case here, this case, this will not be true. It's not even. We come down here. What we're going to do is we're going to call ourselves recursively like this. Doesn't matter what the value is, but all these things are constant time except for the recursive call. So constant time, that's your constant here. Notice this is the same. We just added 1 constant to this. So I've basically taken this thing here, this line here. I've added a constant to it and then changed the t1 into a t0. Does that make sense?
Partly.
Okay, let's do it again.
Yeah.
T of 1 plus log base 2 of b times c. So that's what we have. Now we want to just expand this guy here. So this guy here will be t of 0 plus constant plus log base 2 of b times c. Right? This is what t of 1 is. Right? And you can see that from the code. And then all I did here is I put the 1 into the parentheses like this so I could group it.
Oh, yeah, I see.
Good question. Yeah. I mean, it's good to watch someone doing a proof like a hawk because we could, it's a collaborative process, right? There's no absolute truth for proofs. We're trying to convince our interlocutor that something is true. Okay. All right. So we have a pattern now. So what do we need to do next? Well, I need to tell you finish the analysis for the case, and you've been very kind about this. I need to finish the case where b is not a power of 2. And I'm going to tell you the answer, and this is actually a rigorous answer, but you may wish to think about it and work out some of the details. So here's the argument. Consider the case where instead of b being a power of 2, b can be anything. So in the worst case, we're going to double the number of recursive calls. So basically, the worst case is where we take the else branch every other time. Why can't we take it every time? Well, that has to do with the property of numbers. And so the little theorem that you can prove about this, and I urge you to do it, looks like this. So the claim is that basically, if you have an n, that it's impossible for n minus 1 and n minus 2 to both be odd. And therefore, you can't recurse all the way down to the bottom on the else clause. So let's write that down, if we had any doubt about it, like this. So I'll write it down as claim and odd minus n1 odd minus n2 is equal to false for all natural numbers where n is greater than 2. And this you can prove by induction. So because it's impossible for both n minus 1 and n minus 2 to be odd, in the worst case, if b is an arbitrary number, I'm going to take the else branch every other time. I can't take it every time because it's impossible for n and n minus 2 to both be odd. But in the worst case, I'm going to double the number of recursive calls. And if I do that, I get a complexity that just looks like this. All I do is add another 2 out here. And 2 is a constant. And so my complexity is still log b. So this is a very common strategy for proofs, although you have to kind of find a trick, which is that you prove an easy case first, like the case where it's a power of 2, and then you generalize to the harder or more general case here. So again, if b is a general number, at worst case, we double the number of recursive calls, even if we take the else branch, which is here, every other time. And the reason it can only be that many times is that as we're decrementing b, it's impossible for both b minus 1 and b minus 2 to be odd. So by the time we get to fast times 1 recursion down, then we'll take the even branch. Now, the next time we might take the odd branch again, you'll at most double the number of calls. So that's pretty cool that we can do that. All right. Now, logarithmic, let's ask ourselves, logarithmic versus linear time makes a huge difference for big numbers. And actually on the course website, for the lecture notes, I put some timing results from a fairly old PC. I typically run state-of-the-art machines in my lab and an old PC at home because I don't like to update them and change all the software. But even on an old PC, in milliseconds, if you look, you could find that things run really quickly. Okay. So logarithmic time algorithms are far faster than linear time algorithms, which is pretty cool. And we've just proved that fast times, even for general inputs, is going to run asymptotically in linear time. Okay. Now we have a little time left, and what I'd like to do is go back and I'd like to prove our claim about logarithms, because I think that was a little fast. I'm sorry, I don't think what I did was too fast, but it was too fast to see the proof argumentation. Of course, you may have a different opinion. So let's prove this little lemma about logarithms, and then we'll sort of sum up. And I think it's useful for us to see these proofs and see how it works. So remember, our claim is that's basically this. I'll generalize. We sort of showed an example for log base 2 and log base 10, but our claim here about logs, because we always want to write just order log without bases, we want to say that log base a of x is equal to log base b of x divided by log base b of a, where a and b are constants. So how do we do a proof like this? Well, let's just do it kind of by construction. So I'll define an intermediate variable called y, which will be equal to log base a of x for convenience. And once I have y, I can exponentiate it. So I can take a to the y like this. Good. And that a to the y is obviously equal to a to the log base a of x. These are just inverses, so that's just equal to x, which is good. So rewriting that, I have a of y is equal to x here. Now I can log both sides. I can say log base b of a to the y. That's equal to log base b of x. Good enough. Now I have log base b of a to the y. I can bring the y out in front. I can write y log base b of a is equal to log base b of x. And rearranging by putting it on the other side, that means y is log base b of x divided by log base b of a as desired. And so we could prove this by a little manipulation. So I wanted to point out to you all now is that what's our proof technique here? It's very much like the substitution model. So you could imagine writing this into scheme here. You could say something like ex exponentiation, ay, and substituting things. You could have times y, log, ba, and so forth. You could have various things like this. So basically, the mathematics and the scheme look a little bit different, but they're kind of similar. So the point I want to make to you is that now that you know a bit more about proofs, is that there's a deep sense in mathematics and computer science that every proof is a program and every program is a proof. So our technique here is really a form of the substitution model. We're just doing it in the mathematical domain instead of in the domain of scheme expressions. but it's very similar to what we did before. We're substituting equals for equals here. Okay. All right. So those are the proofs that I wanted to do. And I want to now go back to the tablet and sort of sum up, maybe take some questions and things like that. So just give me a minute to do that. All right, I should be back. Please let me know if you can hear me and if you can see the tablet now.
Yep, all good.
Okay. All right, so one thing I wanted to mention is that I find it very difficult to do anything but the simplest proofs, by typing them. So I like to write them out, and I think you probably will too. But I did write them out post hoc, and if you have any quibbles about the handwriting or what a symbol meant, I tried to write this all out, and they're in the lecture notes. These are already on the web here. So as I mentioned, there's some time results in the lecture notes that we ran. This is on an old PC. For the speed of times1 and fast times as a function of the size of b. And you can see there's a dramatic difference in how fast these things are. And in fact, modern computers use variants like fast times for computations on larger numbers. So to summarize in the last couple of minutes, we did a lot today. We saw techniques for analyzing the running times of our programs, right? Asymptotic analysis when n gets large. And we first saw something really from analysis in mathematics. We saw grows more slowly as \pred in LaTeX, scripty less than. And based on that idea, we have order notation. F is of order G, right? F equals order G, if you will. In this lecture and others, we'll assume constant time primitives. We'll see some non-constant time primitives, in fact, linear time or worse, in future lectures, so you have to be careful about those. And we looked at recurrence relations for expressions. So I have a few questions here. So I said computer science wasn't science to get you interested, but I actually think this is science. So science is about making predictions and having hypotheses. And our theory here predicts the time it will take an actual program to run on an actual computer. And that prediction is independent of the actual computer you use, right? It's pretty interesting. And you can test the hypothesis by actually running this. So basically, a key thing to remember here is that asymptotic analysis, or order of growth, is not really about behavior at the infinite limit. It's a behavior at an achievable large finite n. So it's behavior at a sufficiently large finite value of n. This is something the other sciences don't get. And I've had papers rejected in, initially at Nature and Science and places where scientists publish because they said, oh, I'm not interested in asymptotics when things go to infinity because all proteins are finite size, for example. But the thing is, this is what distinguishes us from the animals. We know that order notation is about behavior at a sufficiently large but absolutely finite value of n. And so the genius of asymptotic analysis and order notation is that it tells you what will actually happen with your programs at a big enough n that's actually achievable on this planet. And this is something that's pretty cool. So I'm actually very interested in the infinite limit for certain problems in mathematics, but this is actually about very practical finite things, which is pretty cool. So if you collaborate with someone who's not a computer scientist, they might not get this and realize that you're talking about predicting behavior about what actually happens. So the reason this is science is that if you have a theoretical algorithm and you prove its complexity, that prediction is something you can actually test by running it on a computer, even before you've built the computer, even before you've coded it up, even before you've optimized the code. And it will be a pretty decent prediction for a large range of algorithms. And the reason we still have it, really almost half a century later, and still use it, is that it's a decent prediction of what will happen in the future. So that's why I think this actually is a form of science, which is pretty cool. Okay, so that having been said, we did a lot today. We did complexity analysis. I will introduce non-constant time primitives and actually list data structure operations on Wednesday, although you've been seeing a little bit of that to motivate you. And what I'd like to do now is to stop the recording, and I will stay around here. If you'd like to stay and ask me questions, I'd be more than happy to take your comments. So let me go over here, stop the recording, and I'll come back in a second and take any questions. Feel free to stay around. I'll stay around in this room if you'd like to have discussions.